Yeah, hello everybody. Today we have a talk by Valentin. Valentin is currently at the MIT. He has been working in the past on, or I think currently working on making HPC a more friendly environment for people programming it by essentially making Julia work in these kind of environments. I think one of his latest papers was specifically also on quantum devices. And we got into a discussion online on Twitter, actually, where we had a little bit on Sophie's work about kind of face detection. And so, yeah, we got to start to talk about also Julia a bit. And we were curious how Julia's compilation process worked. So we asked him whether he could give a talk, and he luckily volunteered to do that. So today we are going to hear a bit about making dynamic programs run fast in the context of the Julia programming language. So thank you for being here, Valentin, and
thank you for having me.
Take it from here.
Yes. So as Stefan said, I'm going to talk a little bit about what makes Julia different from other dynamic programming languages, how its design choices allow for static compilation, and how that impacts down the road things like performance, usability, some of those trade-offs that crop up. So if you have never heard about Julia, why would we need yet another high-level language? Right? We have Python, we have Ruby, we have MATLAB, we have all of these other high-level languages that pride themselves on being more user-friendly, more accessible, faster time to solution in terms of sitting down and actually writing complicated programs or allowing the user to focus on algorithms. So why do we need yet another high-level language? So Julia has the typical features of a high-level language. It's dynamically typed, which is both a boon and a problem. It has a high-level syntax. It, as many other modern languages, is open source with the MIT license. It has a built-in package manager, so no longer any conda woes, and it excels as interactive development. Here on the right, we have a very small Julia function that basically just computes the Mendel set. And you can see, syntactically speaking, we don't have syntactic white space. So the blocks are terminated by an end statement. We have inclusive ranges, not exclusive ranges. So there are small differences from other languages where Julia takes more of an inspiration from other numerical focused languages like MATLAB and Fortran. Yeah. So what are the unusual performances of Julia? Well, on the one hand, it has a reputation for great performance, and that varies, right? Performance is always dependent on what the user wrote, and you can always write slow code. But Julia also allows you to write very fast code that can compete with any other programming language. It has this interesting ahead-of-time, just-in-time compilation style that we will talk about. What I personally quite like a lot is that most of Julia is actually written in Julia. So I can start at a high-level function like MapReduce, and I can start exploring how that function was chosen to be implemented. And I can explore it all down to the lowest levels and see what everything did in that chain of function calls. And I don't have a sudden stop where it's, oh yeah, it's calling a C library. We still use C libraries aplenty, especially for matrix routines, like everything that is PLAS. But a lot of Julia and even large parts of the Julia compiler is written in Julia itself. And it has very powerful reflection and metaprogramming capabilities. And jokingly, if you have ever heard the term mLisp, Julia is that incarnation, a Lisp that is written in a C-style syntax. This is an old plot. I should probably find out a new one, but this is one measure on our benchmark set, and as all benchmarks and all, especially micro benchmark, take this with a grain of salt. These were written to exhibit patterns of programming and to show that depending on how you choose to implement your program, you can either have very good performance, but that performance spread can also vary widely, right? Most programming languages can be fast on some of these benchmarks. Like as an example, Octave is using a fast matrix multiply, but then on the other hand, if I'm using a recursive Fibonacci implementation, I'm getting quite bad performance. And the point here is more that the spread of Julia is quite low. So I mentioned Julia as a dynamic programming language. It makes sense to step back for a second and think about what does dynamic actually mean. Commonly, we refer to it to the type system. And so the type system is semantic. What that means is, if I would say the language is static, that the types are checked during compile time before I run the code. Dynamic means types are checked on the fly during the execution of the program. This mostly refers to, do the types of a variable stay constant or can they change during execution? So if I have a variable x and I'm assigning different types to it, is that permitted by the language or is that disallowed? What it also means is, do I have closed world versus open world semantics? And that's something that mostly gets forgotten in this discussion. Closed world means all of the code that a program is going to run exists at the time of starting the program. Open world means the program itself can add code to it. So if you want to do a quick litmus test, is most dynamic programming languages have some form of the eval statement. I can evaluate a string or an expression at runtime, and that will change the code available to the program itself. So I can add new types, new functions, new methods at runtime. And a third one is that is mostly starting to become an implementation question, is the struct layout static or dynamic? As an example, in Python, classes or class instances, even worse, are actual dictionaries, implementation specific. And I'm not sure anybody sat down in the beginning and thought this is a great idea. It is more an implementation detail that leaked into the language semantics and is now part of the language semantics. But I can change, I can add and remove fields at runtime per instance. Right, and here on the side, I have a small Julia program that has indeed like dynamic typing on the variable x. Right? X in the beginning is Boolean, and then depending on whether or not I execute this condition, x will change to a string. I can still statically reasoning about these types, but the runtime semantics are that depending on the execution of the program, x has a certain type. And for me, this is one of the realizations that took me quite a long time to actually get to, is that while we focus in programming language theory on the type system a lot, that dynamicism, or what it means to be a dynamic programming language, is a broad spectrum. And you can make a choice to be on that spectrum towards between dynamic and static, and decide I'm gonna make certain choices for my language semantics. And one of those choices Julia made, and that it had quite profound impacts, is that we have open world semantics, we have dynamic types, dynamic variable types, but our struct layout is static and final. And I will comment on what that means in a little bit. Okay, so Julia is all about avoiding runtime uncertainty, which is kind of funny, because as a dynamic language, the dynamic semantics introduce runtime uncertainty. So we have a type system that is quite sophisticated. And we use that type system not to prove correctness of programs, but to improve performance and drive multiple dispatch. So type inference is used to discover types in a program. Multiple dispatch is multi-methods, allows us to be not object-oriented. So a function you can choose which implementation of a function to call depending on all of the types of the arguments, not just the first type. Then we do quite aggressive specialization on the types being passed to the functions. And because of all of that, we can make use of JIT compilation. So this is the Julia compiler pipeline. In like its biggest step, we start with the input program, and we translate it into an abstract syntax tree. And that is the first thing programmers can actually interact with. So we have macros, and macros are functions that take in an abstract syntax tree and produce an abstract syntax tree. That then gets lowered and linearized. We perform inlining and type inference over that lowered AST. Now we have a typed AST. We can do some optimizations here, and then we perform LLVM codegen. So LLVM stands originally for the low-level virtual machine. It is neither no level nor a virtual machine these days. So that LLVM codegen is the translation into this common intermediate representation and allows us to efficiently target all of the different hardware architectures out there without us having to write compiler specifics for like supporting PowerPC. We still have to make the runtime run on all of these platforms, but we don't need to develop a specific code generation process for that. And LLVM is being used by Rust and Clang and Flang and all of these other newish compilers. LLVM itself then will run quite a bit of optimizations over code. It will then do something called a translation from middle end to back end, where we lower it to machine IR. More optimization are being run over that machine IR. Now we need to do things like register allocation, and then we do native codegen, translate it into actual instructions, link those in memory, and then execute them. I mentioned that Julia has introspection. This also leads to stage programming. So if we are operating on the level of code, Julia programmers can write string macros that allow them to implement their custom parsing. So there's some examples out there where somebody has a string macro that takes in Python code and has a custom parsing handling and execution handling for that. And so every time you see an @ sign in Julia, that's a macro. So this added, which, allows me to ask the question, which method am I about to execute? So you give it a function call, and it will look at the types currently present, and then will say, out of the 128 multiply calls possible, you're going to execute this one. And that added is then opening an editor and letting you look at the source code at the same time. As I said, that code is then transformed into an abstract syntax tree. That is the level that macros work on. And so you can look at that AST and interact with it. And this add code lowered will allow you to introspect it. The next step down is this typed IR. And on the left-hand side, we have how we can interact with it. So we can use generated functions as a form of staged metaprogramming, where you will get a type signature, and you're responsible for returning a body of a function that matches those types. And why is that very powerful? Well, I can embed values in the type domain. So I can say I have an array of type float 32, so single precision, but its dimensionality is 5. And so I can write a generated function that looks at the dimensionality of 5, and then code generates a loop nest 5 deep to emit the optimal code. And we can ask the compiler what it thinks about this typed IR. It can warn us about things that it might see as problems with code warn type. We can see it before and after optimizations. And then there is more compiler-esque rewrite works passes being happening, and there is a lot of interesting work happening right now in making these interfaces more powerful and give them usable semantics. because as soon as you start injecting compiler parsers dynamically into programs, the semantics of what is actually being executed is quite funny. So we call that non-standard semantics, and cassette.gl is one of the packages that allows you to inject non-standard semantics and, as an example, implement a probabilistic programming language or a quantum programming language on top of Julia. Then after typed IR, we do the translation to LLVM IR. We can directly call LLVM code. So if I have a very specific implementation of a function that is only going to work on a next generation x86 machine, and I know that I'm not quite going to emit that code yet, then I can directly LLVM call that. And so this allows users to interact with LLVM in a quite sophisticated way and implement, as an example, a simd.gl package that allows you to write explicitly vectorized code at the low level. You can inspect the compilation pipeline at that level with add code LLVM, again with optimizations turned on and off. And we have a package called llvm.gl that allows you to programmatically build up LLVM IR and inject it into the compiler. And I'm not going to talk too much about this, but this is how what allows us to retarget Julia to different hardware backends, like executing on GPUs, executing on funky devices like that. We can change what the language means and the implementation of the language runtime by codegenning the appropriate implementation. And then after the fact, we have assembly, and some people really want to inject their custom assembly calls into it. Don't ever do that. It's not portable. LLVM IR is somewhat portable. Assembly is not portable at all. But you can do that, and you can also look at what assembly, LLVM, and Julia produced for a certain function. And this power of being able to introspect each part of the compiler pipeline is something that in the beginning I thought would only be used by compiler authors, but it's something that users actually start to explore, and is something that helped me on my journey from somebody who studied cognitive science and was interested in robotics to somebody who is now working on language runtimes and compilers. It is quite addictive to be able to see transformations as they happen and to explore and iterate on how the code changes. Okay, back to dynamic semantics. So the Mendel function here on the left-hand side, if I were to interpret it, or if I were to not have any information about this type, I could ask the question, the absolute value function for Z has 13 different methods. Right, so the function itself has a set of methods associated, and that set of methods will be dispatched to depending on the type of the argument. So if I know nothing about Z, I don't know which of these methods to call. So intuitively, everything should be a virtual function call. You have the same problem in C++, where you don't know which subclass you're targeting, and so you need to have a dispatch call side there. You have the same problem in Python, etc. So is everything in Julia a virtual function call? And the answer is no. This is where, for us, type inference comes in. So I can call the Mendel function with a certain type for an integer. And this time I'm saying I have an unsigned integer of 32 bits. As a very short aside, you might have noticed that, as an example here, integers have bits. So we target machine integers instead of saying that our integers are unlimited in size. That is unusual for dynamic programming language. And the intuition for that was that this would allow us to produce better code. And allow us to take advantage of things like vectorization, which is quite important. That is true, but we also have things like big integers that are unlimited in size, truly unlimited in size. But it's always a user choice whether or not they want to use those, or whether or not they know that they can't exhaust the available space of int32 or int64 or int128. Right. So on a call, and this I'm using the sign as my examples. I'm going to look at the type of x, which in this case is a float 64. I'm going to look at the whole big method table of sign, and I'm going to look for the method that is going to match the type I'm calling it with. So in this case, it is the sixth entry here, where T is a subtype, the funny arrow-looking symbol, of the union float 32 or float 64. And when I call this function for the first time, I'm going to specialize it, not just on the fact that T is a union float 32 and float 64, but that I called it with float 64 actually, and we're going to compile a specific method for that signature. So I can see that in action. Here I'm getting the method list for all of the methods of sign. I'm now filtering it by the dispatch signature. So I know that the first argument of a dispatch tuple is always the type of the function I'm calling it with, and then the argument types appended to that. So in this case, it's going to be a tuple of type of sign float 64. I can filter all of those signatures of the methods that will match. And what we see here is that from our list of 6, we now have a list of 2. There's still an ambiguity. We don't know which one to call. Either one would be legal, but we now have to make a choice for which of these to call. And the rule in Julia is we will call the more specific one, the one that holds more information than the other one. And so real is an abstract supertype of all of the real numbers. And that has as a subtype abstract float, which has a subtype float 64. So union float 32, float 64 has more information than the abstract supertype real. And therefore, we're going to choose the method for union float 32, float 64. And now when I call it for the first time, and this is the end of the slide, you can see that before I called it, the specializations of that method is empty. There's nothing in there. And after I called it for the first time, I now have an entry in that specializations table that for that specific combination of arguments. Any questions up to here?
Maybe just one quick question. Do you have kind of an upper number of copies of a method you would compile? Do you limit the number of specializations?
So yes and no. So when the type is unknown, we have a heuristic limit for how much for what we call union splitting. So if we know that X could be a union of multiple types, then we will limit when we will split that union statically versus doing a dynamic call into the runtime. If we have concrete types, we will aggressively specialize. And so one of the biggest complaints about Julia often from users is latency, and latency is due to us compiling too much.
Mm-hmm.
So one more question actually. Can it happen that at runtime you are not able to assign a pre-order between the specializations that you have?
Yes.
So in that case, which type would you choose?
Give me 3 slides.
Okay.
Or actually the next slide, right? So this is what I talked about. This is the most specific method. And normally what I do here on this slide is I would switch to my terminal and execute this code for you, because I think that's the most educational, but I can't share my terminal with you right now. So this is exactly the situation you talked about just now. I have three methods of the function f. One of them is specific in y, the other one is specific in x, and the other one is specific in y again, but for a different type. So when I call f with the values 1.0, 1, so a float in the first position, an integer in the second position, I should dispatch to the first implementation and I return 0, right? When I call it with 1, hello, where hello is a string, the most specific match for this is f is the second implementation of f, where I should return 1. Now, the same holds true for the third case, where the most specific one is the one that matches the float 64 in the second position, and so I get as 2. But now this is your question you have had. What happens if I can't make that decision because both the second and the third implementation are equally specific but in different arguments? And what you will actually get is a runtime ambiguity error. So at runtime, we will throw an error, say we didn't know how to disambiguate this call. Please implement a disambiguation of these two methods, and we'll tell you which signature you need to define to make a dispatch happening. Okay, so taking our manual functions again, and now we're gonna turn this wonderful code into something illegible, but that the compiler likes more. And so on the right-hand side, we now have the output of add code lowered, which is the linearized intermediate IR representation. And if you work on compilers, you know the terms static single assignment. So anything that starts with a percentage sign is an SSA value. You also have all of the basic blocks listed. So we have a basic block 1 that ends in a goto statement. We have a basic block 2 in a goto statement. Basic block 3 ends in a return statement, 4 in a goto, and so forth. And yes, goto statements exist in the language normally, but please don't use them. They're still considered harmful, except for the compiler who really likes them a lot. And so these basic blocks, they form our control flow graph. And we have variable assignments. So this set at _7 equals set _2. That's a variable assignment. The C equals at set at _7 is also a variable assignment. And so you can, if you look closely enough, you can see the entire structure of the code that I just wrote on the left-hand side represented on the right-hand side. And on this code, we will now run type inference. So we will start with the input arguments, and we will use abstract interpretation to propagate that information down through our program. And oh yeah, and the one thing you might wonder about if you've never seen this kind of code before is how the heck are for loops implemented? And for loops or loops in general are implemented as back branches. And so you can see here in basic block 5, the goto statement to basic block 2, that is a back branch. And if you look at the code closely, you will see that we execute the condition whether or not to execute the backwards branch or not. Right. So Julia's type inference will now run over this intermediate representation. It performs a data flow analysis. It is abstract interpretation based. And the challenges for abstract interpretation in general are within functions, how do I handle loops correctly? And across functions, how do I deal with recursion? And this across functions is actually like the most complicated part. What does it mean to be abstract interpretation based? Well, we will be iterating our type analysis to convergence or until our heuristics say that there is no such thing as convergence possible anymore. We could run forever. Why could we run forever? Because users could write code like here on the downwards left side, where I have a limit function, where I say, if I see the value 1,000 in the type domain, I will return 1,000. And if I see any other value, well, I will just increment n. And so if I start with the value 0, in theory, type inference could run all the way up to 1,000, execute this code in the compiler, figure out that statically the output will always be 1,000, and embed that into the IR. We choose not to do so because, but you can see that we did some iterations, right? We did 1, 2, and 3, and then we realized that no more information was being discovered. So we stopped and we placed a dynamic code there. In contrast to, on the right-hand side, we have the same function with the only difference that I now decrement instead of incrementing my values. And so if I start at a limit value of 2,000, it actually will run this code up until convergence to 1,000. And you notice this because compiling the code on the right-hand side actually takes noticeable time, versus compiling the code on the left-hand side does not take noticeable time. Now, you might think, why the heck is there different convergence rules for subtracting and addition? And that has to do with the kinds of programs people write in Julia. And so, as I mentioned, the arrays have the dimensions in the type domain. So I can write cases where I look at ever smaller subdivisions of that array with lower dimensionalities, and I will converge to a 0 at some point, and not go behind 0. So these kinds of like doing arithmetic in the type domain are like not looked upon kindly by us compiler authors, but supporting them is indeed necessary. And you can take this to an extreme, like if you have a couple of minutes this evening, you can take my implementation of piano arithmetic and see whether or not the first or second argument is expanding, is bigger than the other one, will lead to the compiler making different dispatch decisions. Generally speaking, if I look at a program, so at the very top, I have a very simple program F. Again, that is just having one conditional branch. At the end of the conditional branch, we say normally, due to abstract interpretation, that X is either a bool or an int. It is of type union bool int. And so if you know what abstract interpretation is doing, you can see that how our lattice is structured. But I don't think I have time to do an impromptu lecture of abstract interpretation today. And so now that I run all of these analyses over my code, you can see that Julia starts annotating it. And so the : always means is type. And so some of our compiler implementations is leaking through here, because we can say that the max eta variable is indeed a constant of 80. And 1 to max eta is indeed a constant of 1 to 80. And so you can see that we're doing constant propagation as part of our abstract interpretation compiler, and how all of the types being propagated through the code in order to analyze it and then optimize it. After we figured out all of the types, we can now perform inlining. And we do inlining ourselves and don't rely on LLVM to do that, because we have more knowledge about semantics, and because inlining will change some of the considerations we need to do later. And so when I turn on optimizations, it is now doing inlining, and the code got a lot more simple. And the only thing remaining are these core intrinsics. Core base intrinsics. And these intrinsics directly map to almost machine instructions. And you have phi nodes, and so that is again one of this SSAIR constructs. Phi nodes unify values coming from two different edges of the control flow graph. This was not intended. I'm sorry. Right. Yeah. So the optimizations we perform on Julia's IR is type inference. This allows for union splitting. Union splitting is important because you might have spotted with eagle eyes that down here, the add_5 equals base.iterate is actually a union of nothing, comma, tuple int 64 and 64. So we're gonna split that small union into its two constituents and turn that into a control flow edge. We recently, since Julia 1.7, are now doing conditional type information propagation. So if you have situations like the little snippet that I showed multiple times, where you have a control flow, where you have an if statement, and that if statement is conditional and it changes the value, the type that you would be returning, while you might not have enough information to make the decision, oh, it is indeed going to be this type, because I see the constant, we can propagate that constraint upwards into the caller, and the caller can make use of that constraint. We perform constant propagation. We now, since Julia 1.8, which is going to be feature frozen today, perform side effect analysis to figure out whether or not a function is mutating memory, is pure, will terminate, things like that. So to make way for more aggressive optimizations. We will perform inlining. And then one other thing that is very powerful is scalar replacement of aggregates. So if you have a complicated struct, if you can discombobulate it into constitute fields, you can open up quite a few optimizations opportunity, and you might realize that you don't actually need to materialize the entire struct. You only ever access and change one field of it. And additionally, coming soon is escape analysis, which will actually then which we already are performing on the LLVM level, but we will also now do interprocedurally in the higher level compiler, so that we can optimize the allocations of a program much more tightly. Okay, so the lessons learned from Julia in some ways is that counterintuitive, or counter to the common use of type inference, is we use type inference as unlocking optimizations, not correctness. And so we use it to find static or near static subprograms. And if we can find these static subprograms, that actually allows for then compiling to a GPU quite straightforwardly. We perform aggressive devirtualization, and some people might say we are compiling too much. Inlining is very important, especially because it gets rid of a lot of the user-defined abstractions. Like, a lot of code is written in Julia itself. So if we can peek through all of the abstractions people are building, we can often find much easier code to compile and execute. And then constant propagation is also something that is just very beneficial, because it can get rid of code that you would otherwise not execute, like arrow branches, etc., etc. One of the problems that doing all of this raises is cache invalidation. Like, as I said, Julia has open world semantics. What that means is we can add code at runtime. Now, if I compile and optimize a piece of code for the presence of, with the assumption that I can devirtualize it, then I need to invalidate that compilation when somebody comes in and redefines my function f. So yeah, as an example, right, constant propagation here, we can constant propagate through the function sign. embed the result of it in the result. Specialization, here I have a function that is using this value type, which raises the length of the tuple into the type domain. And now I can give it a tuple of things that contains many different types. So float 32, and a complex number. And I get specializations of the sign functions for all of the different constituent elements, instead of just having one dynamic dispatch of sign, or three dynamic, a loop over the tuple and dynamic dispatches inside the loop. So, but these are the user can choose to basically write code that does this, but in general you don't need to. The compiler does a lot of the heavy lifting, but you might end up in a very particular numerical kernel where this kind of compiler shenanigans is called for. As I mentioned, cache invalidation is one of the biggest problems. And there used to be a version of Julia back in the days when I started using Julia where we didn't have cache invalidation. And so if I define the function f that returns 1, I call g calls f, and I call g, it will return 1. Straightforward. But now if I redefine f in my REPL session and I still call g, it still returns 1. And that is cache invalidation did not happen. And we have compiled and optimized a version of g. And back in the day, it was basically, I would just restart Julia ever so often so that I didn't see like mysterious side effects from past executions. Nowadays, this is actually tracked in the compiler. We have invalidation edges between specializations. And the big innovation is something we call word age. And there's a research paper on this from, I think, last year that describes this in more detail. But it essentially says a function definition is valid from word age 12 to word age 30, because in word age 30, it got redefined. Why is this range important? Because if you have something like tasks, so code that can execute in different times, we have the language semantics that if I'm changing the code, if I always want to get the newest one, I have to explicitly use something called invoke latest. Invoke latest is an escape hatch that says, I don't want to call the code that is consistent with my current worldview forever. I always want to get the newest version of this code. And other than that, we optimize everything together in these ranges. And this allows us to reason about what functions are visible, what function definitions are visible at any given time. So when you change a leaf node, when you change the definition of a function that is used quite a lot, that can trigger recompilation. And that is one of those like finicky aspects of Julia, where a user comes in and redefines the meaning of convert for every type. And suddenly they are wondering why there is a 30-minute, that's an exaggeration, a 30-second latency on their next function call. Well, you changed the meaning of what everything does, so we need to go through everything and check it again. One design choice I alluded to in the beginning is the decision to not allow struct definitions to change after they have been defined. So we have abstract types that describe a dispatch hierarchy. So I have the any type, and then I have an abstract type number, which is a subtype of that. But then I have a primitive or a struct type int64, and I can no longer subtype from that. And that is in contrast with a lot of object-oriented programming. The other thing this allows us to do, which is very important for performance, is to actually reason about the layout of structs when we compile it to LLVM. So we know that because we have an array of int64, of an array of complex numbers, the complex number is going to be, each of the fields is going to be of a certain size. They're going to be laid out next to each other in memory. So instead of storing pointers to boxes of values, we can store the values directly because we know the type of the we know the type of the elements of the array. So this is what I mean with data can be stored inline consecutively in memory, and that is really important to get your performance and not end up doing pointer chasing. Another design choice Julia made in the beginning is that it has immutability and mutability as different struct types. So you can say when you define a struct in Julia, it is by default immutable. And then you can say I want a mutable struct where I can change the fields at runtime. I can't add fields or remove fields, but I can change the value of the fields. And that is more subtle in its performance benefits, but before we got really good escape analysis, immutable values could always be stack allocated. That was great for performance, and their layout is easier to handle. But I think more profound is actually the thinking of the user level, because immutable values are always copied. So I can differentiate them only by direct comparison, not by pointer. And so when I pass an immutable value to a different user, I'm not worried about them mutating the memory. And whereas with mutable types, right, I have exactly this mutable state that I need to think about. Right. So how much time should I set aside for questions? Probably I have 1 or 2 more minutes, and then we can go to questions. So when we look at JIT design, there is the traditional choice for dynamic languages is called a tracing JIT, and Julia is most decidedly not one of not using a tracing JIT. So in general, when you look at interpretation and compilation, whether or not your language should support either of them, it's not really a question. A dynamic language must support interpretation, or static language is only compilable. There are interpreters for static languages, and there are compilers for dynamic languages. But interpretation often gives you low latency, and if you are in an interactive setting, like a dynamic programming language often is, low latency is great. But it also getting really good throughput is really hard, and that's where tracing JITs often come in. Whereas compilation has high latency, and normally static programming languages get away with high latency because they are compiled once and then always executed that compiled binary, except when you then go into the business of wanting to quickly iterate on your code, and you're always waiting for those 5-minute compile times of your C++ programs. I might be a little bit charred by working on LLVM, but you get good performance. So Julia is ahead of time just in time, which means we will compile at the method level. Every method will be compiled when it's being called the first time. We will cache that code. So sometimes people joke that Julia is fast the second time around, because the first time you feel that compilation overhead. But really, that approach is only profitable for us because we have type inference and we can reason about our code. When you have very highly dynamic user code, it is not really beneficial. And so there's some heuristics there. As an example, if you don't have a loop in your function, we might not even bother compiling it. We might actually pass it through our interpreter. But getting those heuristics right is really tricky. And what people value quite a bit is predictability, like especially when you ask them to use this language to write HPC-like programs. They want to know that their kernels is being optimized. And having worked on Scala and Java programs, like one of the biggest challenges is like, do I need to warm up my just-in-time compiler for 1,000 iterations before I can actually start measuring the performance? When do I measure performance? But maybe I don't even ever execute this code 1,000 times, right? So maybe I need to actually look at the warm-up period of my compiler to figure out my true behavior. Similarly, if I'm operating in a server environment and I'm getting requests, if I need to compile code for those requests, it's a big latency spike and really bad. But then on the other hand, maybe I can warm up my ahead-of-time compiler by replaying the last 1,000 requests I got, and then I have a warm cache and I have very predictable performance thereafter. So there's a huge design space and trade-off that is really interesting to explore. So for me, tracing JITs always have felt more magical. Like, I don't know when it will de-optimize. I don't know when it will re-optimize. And I'm more interested in multi-stage compilation. And so maybe we'll eventually get to that, but that is going to be a huge undertaking, and we will have to guarantee that all of the things that people really like about Julia today will be maintained by making compilation more complicated. For now, our focus really is on improving caching and making sure that we can also cache the compiled code for images, for user packages. And here I will stop. I can make the slides available. I have some more stuff about targeting LLVM and especially how we retarget the language that might be of interest to some of you. If that is, we can chat offline as well. The last thing I would like to say is we have a yearly developer meetup, and it's growing every year, JuliaCon. This year it's going to be on the 27th to 29th of July. And it's going to be virtual, which is sad, but better than having people from all over the world fly to the US.
Yeah, well, thank you very much. Oh, do we have questions?
So I have a small clarification question. So I don't know whether you mentioned anything about the scoping. So I was wondering, is there dynamic scoping in Julia, or is it lexically scoped?
It is lexically scoped.
Lexically scoped. Okay.
So except for closure capture.
Okay. So yeah. So there I could see why AOT compilation could be sort of the choice which you go ahead with. And so also I have another question. So you mentioned that Julia has this eval, right? So you can send in code at runtime and then execute any arbitrary code. So are there situations in which this cache validation thing that you spoke about is required when you have a dynamically injected code, which which is basically calling some existing code which you have already compiled? Could you give an example of that?
So as an example, so there's one important constraint on eval. If you evaluate code from within a function, that function cannot immediately call that evaluated code. It must either return to the top level, or it must use what I call this escape hatch called invoke latest. And so one very amusing use case of evaluating code is like evolutionary algorithms on programs. Right? You have a program that is starting to evolve some code and has some heuristics for beneficial for making progress, and it will call eval all the time. And then it needs to invoke latest. What you specifically talked about was, does cache invalidation ever matter here? And it does actually. So this is the weird interplay where, like, I could eval can change the entire all of the code in the known world of Julia, in the known universe, and so I can change the meaning of plus inside my program. And if the user is running something like a repo and is changing the meaning of plus, then I need, for the next execution of their program, I need to invalidate the entire cache.
Yeah. Okay. I see. So in that sense, yeah. Go ahead, please.
We scope those invalidations by this word age mechanism I mentioned, and so the new version of plus is only seen in the next word over, and so the old code is not impacted by that.
I see. So just, I don't want to take away all the time. So just one quick question. So is there a counterpart of scope chains which JavaScript has in Julia?
I'm not familiar with JavaScript scope chains, so I can't answer that on the top of my head.
I see. Okay. Okay. But yeah, thank you. Okay.
Okay, yeah, present.
Yeah, I hope you can hear me properly. So
Yes.
really nice talk, thank you. I didn't quite know about Julia, so it was quite great to hear about it. So it's just, so you showed us those cool macros that gives information about the compiler pipeline.
Yep.
And I was wondering, what is the extent of reflection in Julia? So you can access the compiler pipeline, but can you modify it?
Yes. So when I was showing there, right. So on the right-hand side of this slide, I have all of the. I'm sitting here writing a Julia program, and I want to interact with it to tell me what the compiler is thinking. And on the left-hand side is all of the. I can mess with that level of the code generation pipeline.
And does it happen?
Yes.
Do people use it? Okay.
To a scary amount. So generated functions are both one of the most powerful and feature I would like people to really stop using. But so there's a climate model, and that will just in time compile its code specialized on the type it sees for the innermost kernel. That is then being executed for the entire time of the program, like the hottest piece of the code. And they have basically a mini domain-specific compiler embedded that takes in the types and produces the innermost kernel. So that things like that I support wholeheartedly. But then other people like me come about, and they want to change the meaning of entire programs. And so cassette.gl allows for quite a bit of munging do we have a good example here? We have questionable documentation quality. So, it allows you for contextual injection of this is a pre-hook that I can say every time you execute a function f, I want to print out all of the arguments. And so now I execute the function division inside this context, and for every function call, I now get to see which function is executing and with arguments. Cool to have, but now imagine people using that to actually build frameworks, and it gets a little bit scary. And there's a real question of composability. Like one of the big cool things about Julia is that because of multiple dispatch, a lot of code composes very well. But then if tools like automatic differentiation or the GPU compiler are using compiler-assisted tooling, composability between those tools becomes much harder. And that's actually a research topic that we're working on right now. As a little side note, because I found at some point I had to debug some user code that was very convoluted and used a lot of these magic capabilities, and I couldn't figure out what actual code was executed. I sat down and wrote a little package called Cthulhu that allows you to statically talk, to have an interactive conversation with a compiler and see all of these decision makings and introspect all of these different levels at different levels of the call stack. Right? These reflection tools all work on the top level. But the question is, now I have a dynamic call, or I have a call inside my function f. How do I get at that function g that is being called and see what the compiler thought about it? So that's the problem Cthulhu is solving, and it is the package I thought nobody would ever use, and it's my most used package. So heuristics and complicated compilers make people want to have better tooling.
Oh, really cool, thank you.
Yeah, I also still have a question. what's the kind of, or how do people write Julia code when it comes to polymorphism? So I assume kind of high-level functions are saying, and maybe the multiple dispatch can lead to all kind of polymorphic situations. So what's your experience there? How polymorphic is that kind of code?
Generally, so multiple dispatch makes for very highly polymorph code. So because right. So if I look at the simplest example is, I think, addition or multiplication. There are 128 or something like that, or maybe 160 different methods of multiplication just when I load Julia without any user packages. So that function is highly polymorphic, and the folks at Northeastern with Jan Witek actually looked at, because there are quite some languages that are tried out multiple dispatch, and some of them removed it over time because nobody was using it. And I mean, Dylan didn't go anywhere as well. But so the question is really, why is multiple dispatch used this much in Julia? And I think it is because we didn't have any object-oriented programming. And so that led to a much more functional approach, much more focused on structs as data containers, and then functions to describe behavior.
Is there any kind of experience, data, or knowledge, or even just a feeling of whether that polymorphism is somehow localized or constrained? So I'm specifically thinking here from the perspective of compiler. Do you basically always resolve the polymorphism if you inline as maybe a fixed level of n or some kind of constant? Or is that something where you may need a more global view on what the program is doing? That's kind of the question Sophie is after.
So I think there is a very subtle question there, and it's very hard to get at. Polymorphism in the presence of recursion. And whether or not the recursive call is polymorph or not. Like if it's just a constant recursion call where the types of each of the recursive calls do not change, everything's easy. But what do you do when, especially in the context of compilation with abstract interpretation, when those types keep changing? Mm-hmm. And so Julia has various ways of dealing with that, and one of them is self-recursion. When the recursion is in the same function, we much more aggressively optimize than recursion across the call graph, where you have multiple indirect calls in between your recursive nodes.
Is recursion used widely, or is that something that's, well, let me rephrase. Is it something that end user programmers kind of use, or is that something that you as a compiler writer use?
So there's, I think,
do you have loops, and are they used?
We have, loops are used very widely. So I think we have loops and they're used widely. I think people go to recursion when loops would be type unstable, because the compiler can actually, because the compiler can deal with recursion much more aggressively than with local instabilities. Mm-hmm. People have been pushed towards White-Tim Lispy code. And this is an interesting, more for experiential question of the design of your compiler change, or what your compiler capabilities leads to different changes in the code patterns you will observe. Which is very funny, because you look at the codes and you go like, I see everybody copied the same pattern that worked very well in this one location. And so recursion in that case is used quite a bit and also in these like kind of code generation-y aspects. So Julia has this, it's called a podcast statement, where if you ever see like a dot plus or dot times, where I'm executing effectively a map over the input arguments, and then the function that is dotted is being podcasted over all of the input arguments. Now, that turns into somewhat of a recursive problem, because I have a podcast, and that podcast is the input to another podcast is an input to another podcast. So when I expand that as a compiler pass, that looks like recursion. And so one of those heuristics we have is a measure, an ill-defined measure of less complex. Are the arguments of the recursive function call converging, getting less complex over time? If so, then I keep optimizing, then I keep looking at the compiler instead of giving up and saying, I'm just going to execute it dynamically.
So maybe just coming back to my question about the polymorphism from a high level. Then you look kind of at the Julia programs that you see, could one say that they often have patterns like, okay, initially we have kind of initialization phase, we build up either data, we load data, process it, bring it in shape, whatever. Then we have a computation phase, and then maybe a reporting phase. So if you see these kind of phases and consider them in the context of the question of polymorphism, do you see these phases doing markedly kind of distinct things? So would there benefit be for the compiler to kind of know about, okay, here is kind of 3 different steps my program is doing?
Yes. So this is something we encounter quite a bit, like especially in like HPC applications where you have what I call the highly dynamic setup phase, where really the program, this is code that we're going to execute once. And it's going to set up the program, types are going to fly left and right. Because on some string argument flag, I might join to solve a different problem. That different problem is a different type. So I will have, at some point, some dynamic dispatch. And then that calms down, and I go into my time stepping loop. I'm going to execute, after like a minute of initialization, I'm going to execute this for 2 days, 3 days. And I would like to change my compiler heuristics based on that. And so that's some people, we have some hooks for doing something like that, where you can start, which is more of the like, you profile your code, you find out where your time is being spent, and you optimize that code. And part of that optimization might be to set more aggressive inference flags and say, I want you to aggressively optimize this for loop, this recursive loop nest, this recursive function call nest, because I know that is actually where I spend most of my time. And it's okay to spend 10 seconds more optimizing if you get it a lot faster. Versus really, I didn't care about anything that I was doing in the initialization phase. And then you have the same thing when you come back out of it and you're like, now I'm doing my data analytics. And you might have intermediate phases, like where one, I have my highly numerical code that is very performance sensitive, and then I have a callback that is doing some error reporting, some outputting some files, moving some data. That doesn't need to be co-optimized with a numerical loop. It needs to maybe be optimized on its own, but it doesn't need to be baked into baked into the optimization. And when I change it, I don't want to invalidate the old code, right? That I already spent half an hour optimizing, right? That I think those trade-offs we have not fully explored yet. How to have the programmer be able to express them in a way that makes sense.
Okay, cool. Very interesting. Thank you very much.
So I was looking for this paper. This is Jan Witek, 2018, where they were looking at how much polymorphism is in the how much polymorphism exists in like a typical Julia function that they were looking at, like the number of specializations per method they find. So there are some methods that are highly specialized, and then most methods only have like one or two. No, the other way around. But you know, so I would. This is the most recent review of like that question of how much is Julia using these polymorphism. So it's performance and designs reconciled by design.
Great, thanks for the presentation.
Completely different question, because I mean, you use the type inference for optimization, but what actually, if you find that there isn't a type, do you actually give error messages then? So does it become like a static type system in some cases?
That there, I'm not sure I got the question fully.
Type inference basically finds that it doesn't have a type. It can't be typed.
So right, abstract interpretation is always allowed to say any. Right? Any, it is any type. I could not find out anything about this type, which is different. So there's also a bottom type, of course. Right? There is the union empty type that says it could not possibly have a type because this is an error call.
Yeah. So what if you get bottoms that doesn't?
That does not bother me much. The union of bottom with anything is the anything, right? Union bottom, comma int is int, and then when I dynamically execute the branch that would have led me to union empty to the bottom type, that is an error branch. It's an unreachable, so that will throw an error.
Yeah.
So errors. Yeah, arrows are defined to have a bottom type, as an example.
Yeah. And so does the compiler ever produce the error, or do you just produce a program that would always produce an error? That
it is, you produce a program that is always produces an error. There is some work by Shohei Kadawaki at the Julia lab, and he is working on static analyzing Julia. So he is then allowing you to introspect and say, hey, by the way, this F will always lead to an error, and here is a report of all of these things happening. So his chat.gl static analyzer allows you to ask these kinds of questions. Would this program always lead into an error?
Yeah, I just thought you would get at least sometimes this information, basically a side effect, and then could just say, oh, well, forget about this program, will always produce an long
yeah, this is a very tempting, and this is what I also thought for like long periods of years that would actually be really viable as a strategy, because I was working on the GPU compiler, and for the GPU compiler we give you that error. Hey, your program always errors. I don't think you wanted to compile this. This doesn't really work in the dynamic execution sense of Julia. And so compiler errors, well, while compiler errors exist, but like these kinds of it will always error is best turned into a runtime error and then found at runtime, weirdly enough, because users don't ever expect that their program could fail at compilation time, and you might never have executed that piece of the code where you found the error.
Okay, it's a different world, yeah.
Yeah, this is also like I always need to basically apologize when I talk to a programming language theorist about the use of the word type inference, because it evokes imagery that is not appropriate. It is really just using abstract interpretation / data flow analysis to figure out the types for optimization, but we must maintain dynamic semantics for execution.
Yeah, does anyone else have a question? Some people already left because they probably have some other work to do.
Thank you.
Yeah. I'm sorry about that. Yeah, normally we would invite for a drink or go for dinner, but well,
the legacy of not having to travel.
yeah, exactly. So she's advice. Yeah.
No,
Yeah.
thank you for having me, and I'm always reachable by email. And at some point, I need to add Julia to the benchmark suit that Stefan is working on.
Yeah, thank you very much for your talk.
Thank you very much. Yeah.
Bye bye.